Hi, I'm Noah Wardrop-Fruin. I'm officially the chair of Joe Osborne's event we're here for today, which is an honor. We're going to do this in a series of stages. So the first stage will be a presentation by the candidate, during which I hope people, unless it is urgent, can hold their questions. Then we'll have a time for questions from people who aren't members of the committee. Then we will send people who aren't members of the committee out, and we'll have an extensive period of time for questioning by the committee. Then Joe will leave the room, leaving only the committee, both virtual and physical. And eventually he will be called back in to hear his fate. Any questions before we begin? All right, let's give Joe a warm welcome.
Thanks, Noah. Thanks to my committee for showing up. I'm Joe Osborne, and I'm here to propose a dissertation. The topic is applying operational logics for the compositional specification and analysis of games. I'm approaching 3 research questions in this dissertation. First, how can approaches based on operational logics contribute to automated game understanding? Second, how commitments to operational logics can support the formal specification of game designs. And third, how these kinds of specification methods could support the scalable verification of games and game programs. The central claim of my dissertation is that applying operational logics can make these tasks, the analysis, specification, and verification of games, more accessible, efficient, and effective. I think this also generalizes to other interactive applications, but their operational logics haven't been explored as thoroughly, but of course they do have them. And we'll talk more about what operational logics means exactly a little later. First, some background. Formal verification is really hard. There's maybe a few thousand people in the world who can do it for full-size real applications in the wild. And it's hard because we have to do formal verification of programs written in general purpose programming languages, about which there are well-known results that say you can't say anything with authority about those kinds of programs. This general purpose programming language thing wouldn't be so bad, except those of us writing verification tools have to write tools that work for arbitrary programs. If we knew more about the programs that we were verifying, we'd be in better shape. But as it stands, we have no idea what some arbitrary general purpose program might do or what it's supposed to do. And asking the people who are writing those programs to tell our tools is not tenable, because actually specifying what a program should be doing is extremely difficult. It's probably harder than the verification task itself. Now, all's not lost, because for certain classes of programs, like interactive programs without loss of generality games, are not completely arbitrary, and we do know some of what they might be doing. Game software has certain conventional properties. Even turn-taking games want decent frame rates to remain responsive. Most games don't last forever, or if they do, that's some kind of degenerate case. Games require interaction, which means they need to regularly get inputs from a keyboard or a joystick and react based on those inputs. This is a natural point for verification tools to intervene. Games usually emulate time frame by frame with a fixed frame rate. It's not always true, but it's often true, and it can be a good simplifying assumption. Most games don't make substantial use of the network or of non-static files on disk in their moment-to-moment play, and they rarely communicate with outside processes, except maybe renderers. And best of all, if we can get verification working for something like Unity or Unreal or Twine, then we can apply that to all the games written in those engines. So we have a lot of leverage here. So interactive programs aren't completely arbitrary. We know some of what they might do. And games are explicitly designed. Like, game designs are these artifacts that exist in the wild. Game designs are robustly theorized with all kinds of formal structures. A popular one is the mechanics, dynamics, and aesthetics framework. Games have genre conventions, which are like constraints on what makes sense to happen in a particular game according to player expectations. And games also have a compositional semantics. Game designers often talk about building games out of smaller games or interlocking subsystems. Before I go much further, I want to talk about game mechanics a little bit. These are very broadly used in AI systems that talk about games, or in formal treatments of games. But I'm not convinced that mechanics are really like a fundamental atom of game design. If you look at something like collision handling, if you have 3 different kinds of objects and 3 different kinds of action that can occur, does that mean you have like 27 different possible collision mechanics? There's like some commonality here that's not captured if you say that each instantiation of this template is a different rule, or like, is somehow fundamental on its own. If you look at character movement, jumping is very similar to flying from the standpoint of code, from pretty much every perspective except how it reads to the player. So they're really built out of the same components, even though they read very differently. And this is even more evident when you look at resources like health or points or ammunition or experience points or what have you. In many cases, it's like literally the same programming language statements that end up reading very differently to players, and end up, there's all this shared structure between these game mechanics that isn't accounted for by just saying that a game is a big set of mechanics. As it happens, we have, I think, a better grounding in hand in the form of operational logics. Operational logics connect fundamental abstract operations with how they are understood at a human level. So in other words, they underlie mechanics. Mechanics are built out of the operational logics in a game. Saying that a game has a particular operational logic, like a collision logic or a physics logic, entails that the program has a set design space of possible mechanics, and that these mechanics are somehow surfaced through observable phenomena and enacted somehow in the code. Furthermore, the interpretation that a game has a particular operational logic has to be maintained during play in order to be coherent. That is, there are constraints which prevent the interpretation from breaking down. So we have a lot of structuring information about how the game should act just based on what it's built out of. This knocks out 3, or at least mitigates 3 of the difficult things about formal verification. Moreover, operational logics link behaviors of game programs with properties of game designs. I think that this could be an end run around the difficulty of specifying games or the desirable or undesirable behaviors of games. I think it could be more palatable to game designers than current techniques that are based on formal logics or things like that. So the claim of this dissertation is that applying operational logics can help with analysis, specification, and verification. There are 3 specific application areas where I think approaches based on OLs could make a difference. Automated game understanding. There are 3 projects I'd like to pursue here. First, the theory of operational logics is not complete enough to use for the purpose of automatically deciding if a game is about a certain thing or has a certain rule, because OLs, as a game studies theory, aren't equipped yet to talk about the combination of multiple operational logics working together to build larger interpretive structures. There also isn't an authoritative list of what operational logics are out there and what exactly they comprise. So there's some paper writing that has to happen there. With this further developed theory in hand, I'll be working on 2 computational projects. First is reverse gameomatic, which takes a game generator that purports to produce games that have certain meanings, and instead takes the games that it would have generated and infers what the original meanings might have been. So it automatically interprets games for their rhetorical arguments or their sense. The second project is Mechanic Miner 2. Oh, by the way, Gameomatic is previous work by Mike Trainer and Brian Blackford and others. Mechanic Miner 2 follows on from Michael Cook's work on automatically generating game mechanics. This is intended to be a minimal intervention that replaces that tool's vision of what a game mechanic is or what games are made out of with a version based on operational logic and particularly authorial affordances to try to resolve some weaknesses in that tool. The second application area is the formal specification of game designs. Here, there's a little bit more theoretical work that tries to, whereas the argumentation techniques of the previous research question were informal, kind of plausible reasoning. Here, we're looking for more deductive reasoning. So we need to map operational logics onto formal mathematical logics or models of computation. There are three computational systems I'd like to explore here. First, with Adam Somerville, is a game-making tool for graphical logic games. Graphical logics are roughly what you'd find in an arcade game or an NES game or something like that, something privileging like sprites and physics and movement and simple resource logics. Next is a formal model of the ensemble social physics AI, whether it is its own operational logic or an assembly of some other operational logics. I think this is important to explore. Ensemble used to be called Comme il faut. It is the like brains behind Prom Week and several other systems from our lab. And finally, I'd like to devise and specify some general safety properties for games that have graphical logics. And I'll talk more about these in the future. The final application area is the scalable verification of game designs and game programs. Even where it's possible to verify a system, sometimes going up from a toy example to a real game or a real program is very difficult because of certain exponential factors. And usually the techniques proposed to get around this are compositional analysis and abstraction. So the three approaches I'd like to develop towards scalable verification using operational logics are first, to enhance some previous work of mine in solving puzzle script levels automatically by automatically abstracting the puzzle script game into a simpler puzzle script game with some relationship between the set of solutions of the simpler game and the set of solutions of the real game. Second, I'd like to use whatever formalism we come up with to address how operational logics compose with each other in attacking questions 1 and 2 in the verification context. So if we can prove a property that's true for some subsystems of a game, can we prove that it's true for the whole game as well? And finally, I'd like to apply counterexample guided abstraction refinement in the context of games using operational logics. And I'll get into what that means later. So this has been a brief overview of the background behind the project and the proposed work. Now we're going to go into more detail. You'll notice that there aren't separate sections for related work or my previous work. I've included what's relevant where it helps to explain the proposed work. If you want to see my 150 item long bibliography, please check out the advancement proposal document, which is in a comment that's been posted to the event website. So, oh yeah, so after the proposed work, I'll talk about evaluation criteria and then the schedule for this work. Automated game understanding. Certainly it's very important that game designers be able to manually understand a game to figure out what its rules are. Certainly players do this as well. And there have been many projects proposed by game designers and academics for recognizing recurring structures or themes or whatever across games. In this context, we can think of these as like reverse engineering tools for extracting a game design from a game's behavior, or a high-level design from a low-level design. In the AI community, there's been a lot of effort on automated game understanding. The general game playing agents often will try to find strategies to games by looking at their rules and figuring out what the objectives of the game that they're being asked to play are, and so on. What's the best way to get points quickly? Matthew Gosdial has done some work this year on automatically recovering levels from Mario games, and also separately some unpublished work on learning the rules of platform games or graphical logic games. And Tom Murphy has some work on learning evaluation functions for arbitrary NES games. The Mechanic Miner project from before tries to find authorial affordances in code to build mechanics out of. Remer van Rosen's recent work pulls out high-level designs and design patterns from a low-level design specification. And there's been some work in transfer learning which tries to map higher-order skills between games, like recognizing in this game what's a treasure and what's an exit, and trying to apply that into other unknown games. All these systems live or die based on their knowledge representations, how it is that they represent the concepts of interest. Mark Nelson's dissertation goes into great detail on knowledge representations in games, and I can only treat it briefly in this talk, but this ends up being very important for the first year research questions. Game engines, game-making tools, game generators, all lean very heavily on knowledge representations. Things that we're used to seeing, like scene graphs or entity component architectures or prototype inheritance or tile maps, they tend to be a little bit invisible. They're not just these like inert features of game engines, but they're actually worldviews that make certain classes of design more central and easier, and others more peripheral and harder to phrase. This is an insight adapted from Agri's work. In general, when we choose to represent the world a certain way, that choice has consequences. In the academy, there are many examples of game generators, game specification languages that all work from their own commitments to what a game is. My choice for what a game is made of is operational logics, as previously stated. The previous representations tend to bracket off how a game works from what a game looks like. On the other hand, operational logics link fundamental abstractions, like when two game objects collide, do some action, or put some game entity into a certain state, with how they're understood at a human level. We interpret sprites touching and then stopping as a cause of whatever happens next, or when we see that a sprite's animation changes, we can infer that the entity underlying that sprite in our mental model of what the game is has changed a state somehow and will act differently. It doesn't have to be a sprite change. It could be a textual description that's changed, or a label that pops up, or a color change of the shadow, or something like that. Operational logics provide to game makers a set of authorial affordances, for example, collision triggers, the altering of physical variables, and to players, and game makers build mechanics out of these authorial affordances. Operational logics also offer interpretive affordances to players. For example, a set of pixels that always moves together when it moves can be perceived as an object with an identity. If objects collide and one of them disappears, we can read this as the destruction of one object by another. And these are how players build up their sense of what the game mechanics is provided by one or more operational logics. These have seen extensive use in game studies through trainers, proceduralist readings. Designers have often used them to explain new systems or new games or new AI systems. The papers describing Prom Week and the Pataphysic Institute all lean heavily on operational logics to distinguish them from prior work. And there have been some AI systems that use operational logics in some ways, including Game-O-Matic, which generates games from an operational logic standpoint. Many of the game makers from before implicitly use operational logics. GameMaker or Unity or Mike Cook's Angelina use graphical logics extensively. Inform 7 or Twine use textual and linking logics. Maybe explicit commitments to operational logics with this theoretical background could improve these tools somehow, or suggest new tools that we could invent. Now, there are a lot of like ands up here, and the composition of logics is still an open question, which we'll talk about a little bit later. My previous work in the area of operational logics mainly comprises a paper I wrote with Dylan Letterly-Ensign and Noah and Michael on how it is that we recognize high-level concepts like combat in games that have no mechanics in common. We analytically derive some criteria that a game has to satisfy to read as having combat. And as far as we know, it was the first work to do meaning derivations with multiple operational logics, or at least with non-graphical logics. This work asserted that operational logics composed to build larger interpretive structures, but not exactly how they composed. So the first theoretical development that we need to work on is getting that list of what operational logics actually exist and what they're like, and pinning down how they compose together. Lots of attention has been paid in the craft of games to the idea that games are built out of smaller games. There's general game playing AI in this area that tries to break a game into subgames and solve the subgames separately. But this breakdown is different from what the game designers use. Game specification languages like micro machinations also aim for a modular approach that builds games out of smaller pieces. And I think that there are places to borrow outside of games for like a theory of operational logic composition, mainly in the domain-specific language community, where there's a lot of attention paid to building languages out of smaller ones, and the formal logics community, which I explore in detail in the paper proposal. My preliminary thinking is that there are about 4 ways in which operational logics compose with each other. First, an abstract operation of one logic may use an abstract operation of another logic, or it may provide an operation for some other logic to use. 1 and 2 are basically dual to each other. Third, there may be logical commitments like game space or game entities or other kinds of concepts that are shared between multiple logics. And game state may be provided by one logic and shared with other logics, or it may be outside of all of the logics and sort of like a substrate on which they're defined. And I'm not sure yet which interpretation is more natural. Finally, there may be some communication channels between logics, but again, this is like fairly preliminary. As for the catalog aspect of this work, I think it'll look something like this. Here's the beginnings of a table for collision logics, not just one, but the family of all collision logics. Any individual collision logic will have some subset of these abstract operations, like altering which objects can collide with which other objects, checking if objects are colliding, performing some other abstract operation, other logic, if 2 other objects happen to be colliding or some other checks are satisfied. Different subsets of these abstract operations yield different collision logics. Since this table is still describing a family of logics, and logics are also distinguished from other based on their communicative strategy, even if they do have the same underlying abstract process, different collision logics might communicate their game state via sprites for each game entity, which are scaled appropriately to the collision volume of the object, or through textual messages that are sent into a log that the player can read when 2 objects bump into each other in a roguelike. So this is there's a broad class of operational logics which can be classified as collision logics. Next, I think it's important to show the interpretive affordances, or at least some of the interpretive affordances of the logics in this family. Collision logics can afford interpretation of the solidity of objects, harm of one object by another, the obtention of one object by another, picking up something by walking over it, the occlusion of one object by another, which implies that there's some kind of 3D space, even if it's just like a integer depth axis, and many other interpretations. And this has to be provisional, but I think it's worth doing at least some of the enumeration of options. Finally, it's a big table, I'm sorry. We need to address the ontological requirements and the ontological provisions of each logic. So a collision logic needs some notion of space. It needs sub-regions of that space. It needs objects which exist in that space, and they must exist at particular positions. But once those are satisfied, it can produce ways of calculating and knowing and talking about the shapes and extents of entities in space based on their collision volumes. So anyway, there have to be some hooks for these kinds of ontological commitments. Phew, okay, theory development over. Now we can talk about fun projects. So Game-O-Matic is, again, this generator that takes a diagram like the one on the left, which shows relations between objects like hunger harms man or time makes hunger, and produces a game which definitely makes that rhetorical argument. So this project takes as input, instead, a Game-O-Matic game and outputs a Game-O-Matic relation diagram. How does Game-O-Matic work? Well, you start from a concept map, like this thing on the left, and run it through this library of micro-rhetorics. Micro-rhetorics are little arguments that connect one of those relations, like harming or following, to some game mechanics. This produces a partial game description, which is structured into a complete game by some set of recipes. We don't need to worry as much about that side of it. But what is a micro-rhetoric? This is like the really interesting part where operational logics are engaged. So a micro-rhetoric is an argument. In Game-O-Matic, it's kind of used in the opposite direction. The arrows are sort of flipped. But micro-rhetorics are ways that we can interpret using these kinds of relations, that some relation holds between objects, or some fact is true in the world that we are creating, based on observed phenomena and cultural knowledge and the behavior of the game. So in this meaning derivation, the green box is the game's behavior. The blue boxes are things that we know as people. And the orange boxes are like leaps of interpretation that the meaning derivation is making. The goal of reverse Game-O-Matic is to build diagrams like these to justify the relational diagrams that it's producing. In effect, what I'd like to do is to mechanize the rules of inference of procedural things. This leans very heavily on this, this notion of concept assignment, which is a very old, very well-acknowledged task in automated program understanding. The key idea is to identify concepts from an application domain, in our case a game domain, like characters, abilities, scores, etc., either from looking at the code or from looking at runtime behavior, or both. This is a prerequisite for almost all the automated game understanding work. I think operational logics are a good starting point here because they already explicitly link interpretable concepts to underlying processes. I think this is much better than, we're in a much better position than if we were just looking at source code and game. Specification mining is a much larger field that contains concept assignment. There are some other special cases here. They could all be used for automated game understanding. We just have to reach for them and apply them. These are very active research communities. Learning a game's rules just by watching it requires a lot of guessing. Humans who've played a lot of games are good at this kind of guessing, but they're still provisional guesses and they're subject to revision since they're based on incomplete information and prejudices. Polya calls this kind of reasoning plausible reasoning. It shows up these days in probabilistic logic, and there are many other offshoots. But I think if we're doing automated game understanding, we have to work in this kind of framework. The goal here in reverse Game-O-Matic side that one interpretation of a game's meaning is better than another interpretation of a game's meaning. A natural question to ask, and I think the key question of this work, is how one evaluates one of those meaning derivation diagrams with the orange and green boxes. I spoke a little bit with Sebastian Detterding at FTG about this, and I'm going to follow up with him a little later. I think the key is to do an approach that combines empirical and analytical techniques, working with Mike Trainer, who's I guess the prime mover behind the meaning derivations. The key concerns are to develop aesthetic criteria for these kinds of arguments. Maybe we could do some meaning derivations by hand and then survey readers to say to figure out how much they like certain meaning derivations over others. We could make some that were intentionally specious or bad, or too much of a reach, and see what they think about them. We could also find out if people trained in doing meaning derivations tend to create similar meaning derivations to each other, maybe with a particular rhetorical objective or whatever. The second project is Mechanic Miner 2. I'm looking to do the smallest possible intervention here that replaces its notion of toggleable game mechanics with a search for authorial affordances in the operational logic sense. A key weakness of Mechanic Miner was that sometimes the mechanics it generated made no sense because they weren't tied in any way to the visual appearance of what was happening. So one mechanic it generated would double the X and Y coordinates of a sprite, which has no meaningful interpretation in physical logics. I think that this is an important first step towards game specification mining, which is too big for this dissertation, but I'm really interested in it. The basic strategy is to enumerate for the operational logics that we care to support a strategy for finding the concrete code that satisfies those abstract operations. This may require some dynamic analysis as well as looking at the game source code. That is to say, we may need to find a way to assign blame for stuff that happens in the game to lines of code in the system. And of course, plausible reasoning will play a big role here. The second application area is formal specification of game designs. Games certainly combine many diverse operational logics, and I think game specification languages should likewise combine smaller, simpler operational logic specific languages. The key move here is to identify with particular assemblages of operational logics, mathematical logics, or models of computation. There's been a lot of work with games and logics, in entertainment games and logics in particular. Adam Smith and Mark Nelson proposed axiomatizing game mechanics in first order logic through the event calculus. Chris Martin's recent work suggests axiomatizing operational logics themselves in a variant of linear logic, and then finding proof techniques for particular restricted cases. But I feel that both of these have a sort of one logic fits all approach. Not to say that this is necessary, I'd like to explore a different direction. So when I say models of computation, I'm talking about different ways of phrasing the problems that we want a computer to solve. General purpose programming languages are, as expressive as you like, but this isn't an unalloyed good. Universal computation is notoriously unsafe and difficult to reason about formally or informally. So it's natural to ask, are there some conveniently constrained ways to write programs? The Daphne programming language requires that all loops and recursions can be proved to terminate. This sometimes requires some extra work on the part of the program author. If you want to make web pages, you have a choice between using JavaScript or just using HTML and CSS. Certainly JavaScript is more powerful, but if you can get away with just using HTML and CSS, you know that your page won't crash or have any errors, or it'll have a simpler class of errors. And the performance will be predictable, and hopefully it's easier for humans to understand. So there are some motivations here for voluntarily giving up power when you're doing programming. First off, the less we have to develop and implement new algorithms, the better off we are. This is the main driver behind so-called declarative languages. We want to leave the algorithms up to some better programmer than us. It may also be more natural to phrase a certain problem as some other problem. And if you can do that, then you can take advantage of some good guarantees. If you can force yourself to express a problem in terms of a state machine or linear programming or Boolean satisfiability, you can make strong guarantees about performance, about termination, and other kinds of characteristics. Constrained models can also be easier to understand. Some generally useful ways of talking about computation or of phrasing problems for a computer to solve include linear programming, finite state machines. Richard Evans' exclusion logic was put to great use, and this is weaker than first order logic, but ends up being very good for that domain. And for multi-threaded programming, working in a fork join regime is more restrictive, but also safer than a general shared memory multi-threading kind of model. I think that there are some natural mappings from operational logics to formal logics. Here are a few. Resource logics can be easily mapped onto Petri nets, or in some cases, integer programming. There's a family of spatial logics that would be a good fit for collision logics. Graphical logics, as it turns out, are quite well accounted for by this logic called differential dynamic logic, which is also a description of so-called hybrid automata, which we'll talk about a little later. The key question here is, how do we combine these different operational logics, specific formal logics? If we can find a good mapping between the composition of operational logics as theorized in project 1.t, and find a good mapping from that onto the composition of formal logics, we're in really good shape. There have been some really successful approaches to combining logics. Satisfiability modulo theories is an extremely successful research agenda that's very modular. Monadic second-order logic is a commonly used way to talk about the evolution of states over time. And it can probably be parameterized with theories or embedded into an SMT kind of regime. So there are some good guideposts here. My previous work in this area has been fairly extensive. I've done a lot of game specification languages. Gamelan was based on board game rules and made a strong distinction between game state, queries over game state, and mutations to game state. But it was like too powerful, right? It used a universal model of computation, which made verifying properties of gamelan games really difficult. I also have some unpublished work in a modular game specification language that has like very strongly and strictly defined data flow between modules, and in its procedural part, where game state could be modified, was exclusively state charts or concurrent hierarchical state machines. But the early prototypes I did didn't have great performance, and it was still a little bit awkward to be working at the level of game mechanics. The theory development of 2.t is going to happen in concert with the tool making that I intend to do with Adam Somerville on a game making tool for graphical logic games. Since graphical logics are, as a reminder, are comprised of character state logics, physics logics, collision logics, and some simple resource logics, it turns out that they have a very natural mapping onto hybrid automata, which combine finite state machines and real valued variables. And in fact, the kinds of discrete space, discrete time graphical logics you see on arcade games or Nintendo map very well onto lazy linear hybrid automata or piecewise affine systems. And these are like an interesting special case of hybrid automata. In these constrained cases, there are very efficient algorithms to answer questions like, is it possible for the system to get into a configuration like this? For piecewise affine systems, it's also possible to do parameter learning. So you could conceivably have a tool that lets you pose a query like, please pick a jump velocity for this character so that it can clear this barrier, but not this barrier. It may also be possible to learn a whole ton from observed game behavior, which would have great applications for game rule learning. These kinds of techniques only become available because we took this operational logics approach and found a good formal logic that connected to it with its own rich research tradition. Oh, and as for the user interface of this tool, Adam and I are really excited about using the kinds of envelope diagrams that Steve Swink uses in his book, Game Feel. This is exactly a hybrid automaton. It's a little state machine that gets you from pushing the button to releasing the button. And in each of these states, the differential equations that update the character's velocity are different. It's like you're switching modes on the physics. And even the same state machine with different physical parameters can give a very different perceptual feel. So the work that Adam and I are doing is going to be generalizing this to maybe more variables or more types of events that can happen, more contingent events, that kind of thing. There's a lot of research. Okay, moving on to the next project. There's been a lot of research in verifying interesting properties of game designs. If you just look at the proceedings of FDG or AID or SIG or ICCC, these show up all over the place because it's necessary to evaluate a game to accept or reject procedurally generated content, to do AI play, to do automated play testing, design support, and so on. I think Tremblay's work in this area is very interesting because it maps the problem of designing a safe stealth level onto high-dimensional pathfinding. I think this is like in the spirit of the kind of work that I'd like to do. Plotkin has this tool called PlotX, which will, for interactive fiction games, let you provide a partial order over puzzles and ensure that the game that you've built actually requires that that partial order is satisfied. It's consistent with that, like you can't do puzzles out of order or something like that. The tools that Eric Butler and Adam Smith built for refraction can do things like make sure that players learn the right concepts in the right order and ensure that the levels that are generated for each of those stages in progression don't have any shortcuts that skip over the necessary concepts. So there's a ton of work here, and I don't have time to go through it all. The second project in this area is to formalize the ensemble social physics. The key question is whether there's an automata theoretic or a logical view of ensemble. The point of doing this is to follow up on work that Ben Samuel and I did this past year on automatically verifying properties of games. We have this formalism called placepecs, which is an adaptation of omega regular expressions, which is customized for the particular game or set of operational logics that you're specifying properties about. These are like the sequential extended regular expressions of the software formal verification community, but the syntax is simpler, and it's not tied to programming language or state, but to like high-level game design kind of concepts. So we have to ask if ensemble is its own new operational logic or if it's made up of existing operational logics. I think that the theory development work of 1.t will feed very strongly into this. It will tell us if there are a lot or a few operational logics. And if there are only a few, then of course, then we can look at this more compositionally. The point of doing this kind of formalization is not only to build support for 2.t, but also right now verifying placepecs requires like exhaustive search over all the possible ways that a game could transpire and making sure that the specification is satisfied in all of those cases. But if we can find an automata theoretic phrasing, then there might be like non-search based ways to prove the property over the whole system. Specifying properties by hand, like we're talking about for this ensemble work, is really useful, but it's also quite difficult, even with something like placepecs. You also can't verify properties that you haven't thought about. On the plus side, I think that operational logics, because they're often used in certain ways or because they engage the interpretive mechanisms of players, they might, on their own, weakly imply certain properties. Concretely, something like a character state logic generally should ensure that all of the character states that a designer specifies can actually be reached during play. That different character states should have different graphical representations or other kind of communicative styles, with more different states more likely to be represented differently to players. Collision logics might implicitly assume that characters should never start off colliding with each other, or that dangerous objects should not be visibly obscured. And we can, these aren't like hard constraints that like game if it doesn't satisfy it, but this is advice that we can give to designers that they can ignore or accept. In physics logics, physical entities should stay within like sane ranges, at least within orders of magnitude. Character velocity shouldn't have a lot of discontinuities usually, or the illusion of physics will be broken. Enemies should tend to be slower than the player. In graphical logics, scene should never get so complex that we can't reliably render it at 30 frames per second or 60 frames per second or whatever. My earlier gamelan work was in the context of computational critics, which were exactly this kind of project, but at the time I was trying to solve too many issues at once, and I was trying to do it in the domain of competitive games, which have much more complicated characteristics. They're more complex in terms of the possible scenarios that can happen. Also, I was using the same basic modeling language for games and for the computational critics, the design advice, but it was very open-ended. I think placepecs being more constrained, less powerful, are a better foundation for this kind of computational critics work, in part because they're a good fit for techniques that work with automata or other formal kinds of methods. They don't require search. The final area of exploration for this dissertation is the scalable verification of game designs and game programs. Scaling up verification to real-world systems requires that you have made a good choice for your model of computation. In the Microsoft Static Driver Verifier and the SLAM verification tool that underlies it, instead of verifying like C programs as C programs, they're abstracted into a simpler representation that only has Boolean variables. In concurrency verification, you usually model in a language like Promella or TLA plus or something that is more restricted than a general purpose programming language, because verification on real programming languages is very difficult. Another key move to make to get scalable verification is to break a big problem out of smaller problems. There are also more informal techniques like property-based testing, where you generate a bunch of test cases according to some specification, and the more of those succeed, the more confidence you have that your program is actually working as intended. But these are more like validation than verification. I've done some work in this area already. I made a solver-aided design tool for PuzzleScript games that does heuristic search derived automatically from the game rules. It presented, first of all, PuzzleScript looks like this. It's a tool for making block-pushing puzzle games and many other games, actually. And it uses these rewrite rules on the left to go from, to match against initial states and convert them into subsequent successor states. So PuzzleScript is super cool. I extended that editor with the facility to show designers solutions to their levels and notify them if changes to the level or changes to the rules have invalidated those solutions, like made them shorter or longer or no longer valid. And designers could scrub through the solutions with their mouse to see each step and click to jump to that step in the main player view and keep their undo stack and everything. So it was pretty cool. I did a test with a couple hundred undergraduates this past spring, I guess. I haven't had a chance to analyze the data yet, but I think it's promising work. This tool actually does support play specs, but only validation. It only checks solutions that are found to be sure that the play specs match. Verify that every solution matches the play specs or every play of the game matches the play specs. Doing that is really infeasible if you have to search through every solution in order to make sure that the specification is satisfied. So what I'd like to do here is replace or augment the heuristic search with formal techniques, and in so doing, build up more expertise in the automated abstraction of operational logics. So I'd like to extend this work with some more formal methods. The key maneuver here is to use the perspective of 2.t and 2.a, borrowing or adapting techniques, the study of symbolic string calculi or finite state transducers or rewriting systems to the domain of PuzzleScript. Hopefully being able to apply counterexample guided abstraction refinement in the PuzzleScript domain. What the heck is counterexample guided abstraction refinement? It's like a lot of words and I say it a lot. So this is a relatively recent technique, like within the last 20 years, I think, to verification. The idea is that you have some property you want to prove on a system, but the system is really complicated and it's hard to prove that property. So if you can automatically derive some simpler system and find out if this property holds of the simpler system, you may be able to translate that proof of the property in the simpler system into the original more complex system. Now, in case this involves a guess, right, of like how much to abstract the original system into a simpler one. So you might have to do several trips back and forth, refining your guess, making it a better guess. Maybe you went too abstract at first and you need to be a little less abstract. This is the abstraction refinement part. On the other hand, if one of your guesses is bad, you can use the badness of that guess as a lemma to stop yourself from making guesses which are bad in the same way. So if you're saying like, ignore this part of the system, But it turns out that if you ignore that part of the system, then the property trivially holds. Then you have this new bit of information which says, I can't ignore that whole system. So whenever I abstract in the future, I can't ignore that whole system. This is the counterexample guided part. There's also a story for finding or proving invariance of puzzle script games. We can abandon search, for example, if we need more of a particular object, but we know that there's no way to make more of that object. We can also search more efficiently. We can group levels into equivalence classes rather than treating every different level as a different game state. Invariants are another kind of abstraction since they approximate the game rules. So the second project in this area is compositional verification. If we can verify individual operational logics effectively, but most games are made out of a lot of different operational logics, we need a way to combine these partial, we need a way to prove properties of different parts of the game and then combine them all together, combine the proofs together. For this, I'd like to do some work in an action role-playing game domain. Here you have a natural decomposition between graphical logics and sophisticated resource logics, and also moment-to-moment and long-term gameplay. And I think operational logics are a very suitable way to break down games of this type. Being able to model a whole game, like Zelda 2 or something like that, or a significant chunk of it, could also help validate the answers to research question 2, or the projects that are done in pursuit of research question 2. Here, the composition calculus that was found as part of 2.t will have to be mapped onto a modular verification scheme. We also need to address how properties that consider multiple logics simultaneously can be verified. Here we can borrow from interprocedural analysis, which is a very well-developed theory in program verification. And there may be some interesting work in representing a game play trace as a series of engagements of operational logics rather than a series of player inputs or something like that. More about that, I think, is in the proposal document. The final project, we're almost through. The final project is doing CGAR, counterexample, guided, etc., in the context of operational logics. So composition is like a very special case of abstraction, where you're just ignoring certain parts of it at a given time. If we have this kind of compositional verification, maybe we can also individually dial up and down the complexity of each game's use of of a game's use of each operational logics. So if I have a physics logic and a resource logic and a collision logic, but I only am proving properties that involve the resource logic, maybe I can scale down or scale up the other parts independently in terms of their complexity. In CGAR, there's this notion of an abstraction function, which takes you from a complex system to a simple system. And I think that most of the work here can be done just by finding a suitable abstraction function for each operational logic. Evaluation criteria. Thinking of the theoretical development, it's kind of hard to evaluate theoretical developments. I think that there are some obvious internal criteria, like does it make sense? Does it help support the kinds of tools we want to build? Does it explain more games more completely? For external evaluation criteria, we might want to do surveys of critics or academics and ask if they'd be more likely to use this newer theory or more refined theory, or where they might not have earlier. Maybe they weren't sure where to start or how they could use them. We might also find out if more scholars publish papers that use operational logics after the publication of this theoretical development than before. Of course, this is going to be confounded by Noah's upcoming book, but it's not impossible to evaluate this. For reverse gamematic, we want to show how plausible reasoning based on operational logics can both identify game mechanics and assign semiotic interpretations from a fixed domain to games. Obviously, we want to make sure that it agrees with gamematic, so it can round trip a meaning diagram to and from gamematic. To my knowledge, though, no evaluation of gamematic's core argument has been performed. We don't know that people believe that gamematic's games represent the things that they're supposed to. So any validation of reverse gamematic, if it also agrees with the original Game-O-Matic ends up being validation for Game-O-Matic too. So this is kind of nice. There are a couple strategies we can imagine for validating these kinds of meaning derivation diagrams that reverse Game-O-Matic produces. Do humans agree that they make sense? Do humans agree that that both the relational diagrams and the arguments themselves are reasonable? I think this would be like a really fun evaluation to do. For Mechanic Miner 2, I want to use the original evaluation scheme that Mike Cook did, but it used a small set of manually selected generated mechanics. So it's not clear that redoing that experiment with a different set of mechanics wouldn't be confounded just by the choice of mechanics. So I want to find other evaluation criteria that highlight the search for authorial effort. So can Mechanic Miner 2 generate a good range or a better range of mechanics than its predecessor? If I have a game, some game code with a known set of affordances, can Mechanic Miner 2 find them all? If I have a game with known mechanics, could Mechanic Miner 2 generate all of those mechanics? Since one of the main advantages I think Mechanic Miner 2 might have over the original is that game mechanics would be more comprehensible to players, we could do an analysis, an evaluation where we show players or viewers even, stuff that's happening in a game and ask them to explain what's happening, where the stuff that happens is determined by automatically generated mechanics versus hand-coded mechanics versus Mechanic Miner's mechanics and so on. Formal specification of game designs. The theoretical work here is mainly validated through the projects. Does it actually work? Does this approach give useful results? Internal criteria are things like, does every operational logic actually have a corresponding formal logic? Is argumentation style of reverse Game-O-Matic formalizable in this kind of scheme? Most importantly, maybe, do you have to be somebody like me who has an MFA in games and a computer science PhD, hopefully, to find these kinds of correspondences between operational logics and formal logics? For the game-making tool, certainly we can find out about the expressive range or the performance of verification of these games using the automata-based techniques as opposed to like search or encodings to like answer set programming or something like that. External criteria are like surveys of users who are asked to perform a design task, or whether the games they make are bug-free, relatively bug-free compared to like making the same game in Game Maker or something. For the ensemble formal model, we need it to account for a good portion of ensemble game. So we don't like leave parts of the expressive range of the AI system uncovered by the formalization. We can test whether it's better for verification than searching through possible playouts of a game built on ensemble. And we also want to be sure that this formalization can support the checking of interesting properties, where interesting is determined by Ben. So this is like a case study approach, right? So I'm going to do this formalization, and we're going to see if it successfully caches the check written by our earlier playspecs paper, which says that if you use formal methods with playspecs, you can get efficient verification of game designs. For the safety properties of graphical logic games, it's important that there are actually enough general properties that are useful to make this project worthwhile. To help ensure this, I'm planning to look at games that have been published with bugs or accounts of bugs that have been fixed, or the games built by users of the tool in 2.a, and seeing what classes of bugs appear commonly across different games. It's also vital that these properties be verifiable efficiently and not require a lot of search or a lot of simulation. Finally, designers should hopefully like use this advice in practice. That's like the ultimate evaluation of this work. If I have some idea that maybe these properties are useful in general, but in practice they're actually just annoying, that's an issue, and that would be a bad result. So moving on to scalable verification. Here, the evaluation is easy, right? You just like compare the new thing to the old thing and see what's faster, like graphs up and to the right. Great. So for the puzzle script work, we want to make sure that the solver based on automated abstraction is better than the old heuristic solver. And also that it's better than translating translating puzzle script to C code or the Promella process modeling language and using model checkers for those kinds of things. So we want to be sure that not only that this is a better approach than what we were doing, but better than some other alternatives. It's also important qualitatively to make sure that this abstraction work isn't tied too closely just to puzzle script, but works for all games that use spatial pattern matching logics. Next, to evaluate the compositional operational logic verification in this action RPG domain, certainly there's this open question of whether games actually can be automatically decomposed along these lines, and whether it makes verification more efficient than a monolithic approach that treats the whole game as a single object. We also, again, need to compare against other modeling languages or going to a regular programming language education on that. Another important question is whether verifying for action RPGs is generalizable to verification of other kinds of games that use the same logics in a slightly different arrangement. So a fighting game uses basically the same logics as an action role-playing game, but emphasizes some more, de-emphasizes others. Adventure games, scrolling shooters, they all kind of engage the similar sets of logics. And we'd hope that verification techniques that work for this work for those two. Finally, for CGAR in OLs, do these abstraction functions actually exist, or do useful ones exist for all operational logics? How well can this be combined with the compositional approach of 3.b? Is this more efficient than doing it on the originals? Is it more efficient than translating to Promella or C or whatever? I'm planning to do this work over the next 18 to 24 months. The rough schedule is, in the short term, basically going research question by research question. For now, developing and applying the operational logics theory up until spring. This fall and winter, starting with Adam on the graphical logic game making tool. In spring of 2016, generalizing the work of 2.a, synthesizing it with 1.t, and doing formal specification of games. Continuing on into the summer. From summer 2016 through winter 2016, the formal verification stuff, the scalable verification, beginning the dissertation writing in fall of 2016. This is a really lot of projects, and some of them are kind of big. So I think that it's important to note that I would be very pleased with just the theory development of sections 1 and 2, reverse game-o-matic, the graphical logic game making tool, and ideally the graphical logic safety properties. I think that would be like really nice. And the compositional verification. I think that's like a key contribution that I'd like to see cashed out. I think that the CGAR for OLs would be a great victory lap, but I think that these things on their own would be a successful dissertation. This is the more detailed schedule, and that's my presentation. I'm done. So thank you very much.
Okay, now we can take some minutes for questions from the non-committee members.
And also, we have some remote people who may or may not have been posting questions or things like that.
They've been posting some questions.
Great, okay. So Ben, you can be the question master.
Oh, for another one?
Sure, yeah.
Okay.
So Daniel.
So I'm thinking about the evaluation in the reverse game work. And what's on my mind is that in operational logic, you're trying to connect properties of the underlying system with phenomenologies observed by people. And games are sketches, right? They're systems built to give the impression of something without the full reification of that thing. And so now you're trying to explain, in this case, analogies that were built in the generative direction by game-o-matic. You're trying to assess, is this explanation better than some other explanation? And it strikes me is that you're up against things like common sense reasoning problems,
Yes.
where the properties that distinguish those alternatives are nowhere in the system that you're evaluating. In people's heads and about the world says, oh, well, that's not reasonable because people don't behave that way.
Yes. So I think I can actually successfully punt on this because in Gamomatic, there's this library of micro-rhetorics, right? Which are exactly these kinds of common sense arguments about something happening because of some semantic reason. Since I know that I'm doing reverse Gamomatic and not like general purpose game interpreter, I'm planning to reuse that library of micro-rhetorics, not at like the source code level, but the arguments that are encoded in those micro-rhetorics. So I think that because I have a fixed set of concepts, and because I know, like in a given game, what the objects in that game are, like what their images represent, that kind of thing. I think, like, certainly it's hard, and there's going to be some work in evaluating arguments and making sure that that the system's judgment about what arguments are better than others are consistent with what people think. But I don't think I have to solve all of common sense reasoning. I think I can, if Gamomatic works the way it says it does, then, you know, because Gamomatic creates a constrained set of games, I think I'm not totally in the woods on that kind of generation.
All right,
That kind of argument generation.
Working with respect to a closed set of
Yes,
possible
yes.
explanations in that way.
Yes. Adam?
So on the reverse Gamomatic,
Yes.
I'm like, I think it's very heavily predicated on whether Gamomatic does what it says it does, and so I think that it's probably, that's the first question, because I mean, if Gamomatic doesn't do what it says it does, and like, you know, there's no inter-rater reliability between, like, you know, so and, like, then it sort of doesn't matter whether reverse Gamomatic works, or I mean, or like it's hard to tell, like, because if any explanation is reasonable from a human, then so I'm not. It's probably worth answering that question first before doing reverse Gamomatic.
That's true.
I might make it not.
Sure, yeah. Certainly the evaluation would be like incomplete, right? Like I'd have a proof that I was able to recover whatever Gamomatic's input was. And certainly doing that does require like recognizing game mechanics, some level of semantic reasoning, but since, yeah, I think it would be awesome if Gamomatic were externally validated. I should probably talk with Mike Trainer and others to see if there's like some momentum about that.
There was some momentum a few years ago that got lost.
Yeah.
So, the momentum would need to be
On the other hand, if this does end up working and the evaluation works out, then it's like two birds with one stone, and because these evaluations could construct evidence that Gamomatic is working as claimed.
Well, I find it interesting that the second bullet there, like whether the proposed, if it's recovering the proposed diagrams, the proposed diagrams don't correspond to anything humans perceive in the game. That's what you're pointing at. But with the second argument there, what if it's sort of, there's a kind of evaluation of like, here's a game, here's an argument that means this proposed diagram, and if someone would kind of go, oh yeah, that makes sense to me that you can make that argument about the game. Or, oh, that's crazy, I would never think the game. That's like a different kind of evaluation that's more like how plausible people find the arguments. Yeah. And it's really more what goes on in game criticism, right? In game criticism, it's basically people are arguing about each other's arguments more than they're arguing about the conclusion of the argument.
And this is something that Mike has said too, that his interest in meaning derivations is not like finding objective truth, but is in like getting interesting arguments, like getting interesting discussions. Ben, can we take an internet question?
Chris Martins asks,
hi, Chris.
how does operational logic theory account for distinction between model and rendering? So for example, movement on a top-down 2D map versus movement through a spatial hole in text adventures. Are they the same OL?
No, they're definitely different because the communicative strategies are different. I think that since an operational logic is a tight combination of an abstract process and a communicative strategy, certainly like the way that players perceive what's happening in those different situations is like completely different. Even at the level of abstract operations, or the more concrete abstract operations, like movement through a continuous space is has some like source code level differences from movement through a linked space. Like if the model of space is different, then the engaged logic is different. We talked a little bit about this, I think, in the combat modeling paper, but I don't remember if it ended up I don't remember if it was cut for space, but certainly like in there, like looking at different models of space or object identity, like in PuzzleScript, for example, there's no such thing as object identity at the like simulation level. If you move an object from one spot to another, you're like destroying one object and creating a new one. There's a lot of really interesting open questions here. Yeah, I don't know where I was going with that, but I think it's interesting.
Our recollection was that we noted, yes, they're different. That's
Oh yeah. I think that was what we had to do a lot in that paper.
We identify that they're different. We don't know exactly what that means yet, but they are different.
Yeah, I think we planted a lot of flags.
Yeah.
I hope that was satisfying.
Oh yeah. Matthew Gusdile also just asks quickly, if the slides are going to be available.
Sure, yeah. I'll post a link after this thing is over on the event page. Okay. Any other questions? Anything else you want to hear me talk more about? I can talk about it. I'm trying to put off the committee question for as long as possible.
That's showing.
Oh, he's good. He has 2 new teeth coming in, so if I'm a little sleep deprived or like distracted, that's why. How's Clark?
All right.
I don't think you're allowed to ask questions.
Oh, okay. Okay, great. Thank you, everybody. Please take food on your way out. I don't want to take the stuff home.
Great, thank you.
And for my committee members on the talk, we're going to switch over to the other URL now. Sorry for the inconvenience of all the switching, but that's what we're going to do. Thanks very much. And thanks for all the viewers at home.